From the smallest subatomic particles to the largest galaxies, physics governs the universe we live in. But as we delve into the intricacies of the cosmos, we often encounter misconceptions that cloud our view. Today, we'll break down some of the biggest physics misconceptions and explain what's really happening. Misconceptions about physics can change the way we see the universe. The classic image of astronauts effortlessly gliding through their spacecraft seemingly weightless. It's a captivating sight that has led many to believe that there's no gravity in space. But let me assure you, that's simply not true. Gravity, my friends, is a fundamental force that permeates the cosmos, holding galaxies together and dictating the dance of celestial objects. So, why do astronauts appear weightless? It's not because gravity magically disappears, it's because they're in a state of continuous freefall. Imagine yourself inside a plummeting elevator. You'd feel weightless too, wouldn't you? That's because you and the elevator are falling at the same rate, creating the sensation of weightlessness. The same principle applies to astronauts orbiting Earth. They're essentially falling towards Earth. But their sideways velocity is so great that they keep missing the planet, perpetually falling around it. Here on Earth, we're accustomed to objects coming to a standstill unless we apply a force to keep them moving. Roll a ball across the floor and it eventually slows down and comes to a stop. This is due to friction, the force that opposes motion between surfaces in contact. But in the vacuum of space, where there's no air resistance or friction to impede motion, objects behave quite differently. Once set in motion, an object will continue to move at a constant velocity in a straight line indefinitely. This fundamental principle is known as Newton's first law of motion, also known as the law of inertia. Imagine a spacecraft coasting through the vast emptiness of interstellar space. With no air to slow it down or gravity to pull it off course, the spacecraft will continue on its trajectory at a constant speed, essentially forever. The universe is expanding, a mind-boggling concept that has captivated astronomers and cosmologists for decades. This idea has profound implications for our understanding of the cosmos and our place within it. But what does it truly mean for the universe to expand? Is it like a balloon inflating, or is there more to it than that? It's a question that often leads to the misconception that galaxies are flying through space, like cosmic ships on an intergalactic highway. This image, while vivid, doesn't quite capture the true nature of cosmic expansion. However, the reality is far more subtle and profound. The expansion of the universe is not about galaxies zooming through space at incredible speeds. The expansion of the universe doesn't involve galaxies moving through space. Instead, it's the very fabric of space itself that's stretching, carrying galaxies along for the ride. Imagine space as a flexible, stretchable fabric. As this fabric stretches, it creates more space between the galaxies, which remain relatively stationary within their local regions. Imagine the universe as a giant loaf of raisin bread dough rising in the oven. As the dough expands, the raisins, representing galaxies, move farther apart from each other. As the dough expands, the raisins, representing galaxies, move farther apart from each other. But here's the crucial point. The raisins themselves aren't moving through the dough, The raisins themselves aren't moving through the dough, they're simply being carried along by the expansion of the dough itself. Similarly, galaxies are embedded in the fabric of space-time, and it's the expansion of space-time that causes them to recede from one another. Similarly, galaxies are embedded in the fabric of space-time, and it's the expansion of space-time that causes them to recede from one another. This stretching of space itself is what drives the galaxies apart, not any motion through space. Evidence for the expansion of the universe comes from the observation of redshift in the light from distant galaxies. This redshift is a key indicator that the universe is expanding. Just as the sound of a siren drops in pitch as it moves away from us, the light from receding galaxies is stretched, shifting towards the red end of the electromagnetic spectrum. This phenomenon, known as redshift, provides compelling evidence that the universe is indeed expanding. Quantum mechanics, the realm of the very small, where particles behave like waves and uncertainty reigns supreme. This is a domain where the rules of classical physics no longer apply and the behavior of particles can seem almost magical. It's a world that often seems bizarre and counterintuitive, filled with phenomena that defy our everyday experiences and challenge our classical understanding of the universe. Here, particles can exist in multiple states at once, and their properties are not defined until they are observed. This duality and uncertainty make quantum mechanics a fascinating yet perplexing field of study. It forces us to rethink the very nature of reality and our place within it. One of the most common misconceptions about quantum mechanics is that it's all about randomness, that at its core, the universe is governed by pure chance. This idea can be misleading and oversimplified. While it's true that quantum mechanics introduces an element of probability into our description of the universe, it's far from being a chaotic free-for-all. Instead, it provides a structured framework for understanding the probabilistic nature of particles. In fact, quantum mechanics is governed by precise mathematical equations that predict the behavior of particles with remarkable accuracy. These equations, such as the Schrödinger equation, allow us to calculate the likelihood of various outcomes. It's just that these predictions are probabilistic rather than deterministic. This means we can predict the probability of where a particle might be, but not its exact location at any given moment. Think about it this way. When you flip a coin, you can't say for certain whether it will land heads or tails. However, you can calculate the probability of each outcome, 50% for heads and 50% for tails. Similarly, quantum mechanics provides us with the probabilities of different outcomes for quantum events, such as the position or momentum of a particle. This probabilistic nature of quantum mechanics arises from the wave-particle duality of matter. This duality means that particles can exhibit both wave-like and particle-like properties, depending on how they are observed. It's a fundamental aspect of quantum mechanics that adds to its complexity and beauty. So, while quantum mechanics may seem random and unpredictable at first glance, it is actually a highly structured and mathematically rigorous framework. It allows us to understand and predict the behavior of the smallest building blocks of our universe with incredible precision. This understanding not only deepens our knowledge of the universe, but also opens up new possibilities for technology and innovation, from quantum computing to advanced materials. The probabilistic nature of quantum mechanics is not a limitation but a feature that provides a richer, more nuanced understanding of reality. Embracing this complexity allows us to explore the universe in ways that were previously unimaginable. So, the next time you think about quantum mechanics, remember that it's not just about randomness. It's about understanding the fundamental principles that govern the behavior of everything around us. And in that understanding we find a universe that is both mysterious and profoundly ordered. This duality and probabilistic nature of quantum mechanics is what makes it one of the most intriguing and revolutionary fields of science. EMS-2, arguably the most famous equation in physics penned by none other than Albert Einstein himself. This equation, simple in appearance yet profound in its implications, has become a cornerstone of modern physics and a symbol of scientific genius. It's an elegant and deceptively simple equation that has captured the imagination of generations, representing the ultimate triumph of human intellect in unraveling the secrets of the universe. The equation encapsulates the relationship between mass and energy, two fundamental aspects of our reality. However, like many profound scientific concepts, EMC2 is often misunderstood, its true meaning obscured by oversimplification and popular misinterpretations. Many people think of it merely as a formula for nuclear reactions or atomic bombs, but its significance extends far beyond that. At its core, EMC2 represents the equivalence of energy and mass, stating that mass can be converted into energy and vice versa. This principle is fundamental to our understanding of the universe, influencing everything from the life cycle of stars to the behavior of subatomic particles. It tells us that these two fundamental quantities, once thought to be distinct and unrelated, are in fact two sides of the same coin, interconnected in a profound and fundamental way. This interconnectedness is a key concept in modern physics, shaping our understanding of the cosmos. The equation itself is deceptively simple, but its implications are far-reaching. It has paved the way for numerous scientific advancements and has deepened our understanding of the universe's inner workings. The E represents energy, the M stands for mass, and C is the speed of light in a vacuum, a constant value of approximately 299,792,458 meters per second. This constant is crucial because it signifies the maximum speed at which information and matter can travel. The equation tells us that even a tiny amount of mass can be converted into an enormous amount of energy, as the speed of light squared is an incredibly large number. This principle is the foundation of nuclear energy, and has profound implications for our understanding of the universe's energy dynamics. One common misconception about E equals mc2 is that it implies that mass can be instantly converted into energy. This oversimplification leads to misunderstandings about the nature of the equation and its practical applications. However, this is not the case. The conversion of mass into energy is a complex process that requires specific conditions and is not as straightforward as the equation might suggest. The equation simply states the equivalence of mass and energy, not the ease with which one can be converted into the other. This distinction is crucial for a proper understanding of the equation's implications. Converting mass into energy is not a simple process. It involves intricate reactions and conditions often requiring advanced technology and significant energy input. This complexity underscores the profound nature of E equals mc2 and its role in the fabric of our universe. As we've journeyed through the cosmos, debunking misconceptions and uncovering the truth behind some of the most fundamental principles of physics, one thing has become abundantly clear: the universe is full of surprises. It's a tapestry woven with threads of wonder, mystery, and profound beauty, constantly challenging our assumptions and expanding our horizons. Physics is full of surprising truths, and understanding them changes how we see the world. What other misconceptions have you heard? Let us know in the comments. Like, subscribe, and share for more physics breakdowns.